All right, you made it to week 2. So we're done with heredity. We're moving on to a new MT. We're going to cover population ecology. So today we're going to go through some basic vocab, a couple of the math problems, and then look at some of our charts and graphs for this unit. So first, before you go any farther, you want to go back to Canvas and have 2 screens open. There is a note page you're going to want to type into as you watch this presentation. So go back to Canvas, open up the population ecology notes. They should look like this. The way I pushed it out is everybody should be able to type in the notes as you go, and it should say, sorry, that was my dog. All right. So what I suggest too is have the 2 windows. So set your computer open so you can see 2 windows at the same time and not have to keep going back and forth. All right, so let's start with some vocabulary. So first, what's a population? So a population is all the organisms of the same species living in the same area at the same time. And that's key, especially the area, because you could have a species of white-tailed deer in Michigan that's the exact same species of white-tailed deer in Montana, just making it up. But because they're not in the same area and not able to interact and breed with each other, they're not technically in the same population. Same species, different population. So population density and distribution. Population density is the number of individuals per unit area. So when we calculate that, it's population divided by area, just like you calculated density before in science or in math class. How many do you have versus how much area are they in? Population distribution, however, is the pattern of dispersal of individuals across an area of interest. So that's affected by a couple things. First, the availability of resources. So whether abiotic or biotic, all those factors in an environment that you need for life will determine where the population exists. So having access to light, water, space, mate, food, all those key resources could help determine where a population exists. So again, population distribution is that pattern of dispersal. So how a population is spread out. There are 3 main distribution patterns, and they kind of make sense if you think about the names. The first is clumped. They're clumped together. So it's where species are together is better. So living in a pack or a family or a herd is better than individuals. So species that exhibit this are herding animals like elephants, where they travel in a family, they take care of each other's young, they work together. Fish who school, so those massive groups of fish that are the same species that travel together in schools. Or wolves. Wolves hunt in packs, they reproduce in packs, they survive better together. So when you look at those distributions, you're going to see a lot of individuals all very close to each other. They're clumped, they travel together or exist together. Next one is uniform, and that means they are equally or uniformly spread out. Sometimes this happens purposefully by man, so humans tend to make uniform populations, especially when you think of like trees in an orchard or rows of corn in a field. They're nice and equally spaced out. Sometimes this happens in nature with territorial species. Species like birds of prey will sometimes have large territorial areas that are theirs to hunt in, and the closest individual of the same species are going to be quite far away and spread out. So uniform, they're nice, spaced out, and pretty uniformly distributed. The last one is random. And these are populations where there's no pattern to where the individuals are. Resources are not scarce, so it's not a matter of they all need to be close to resources somewhere. And it's just really kind of scattered. So trees in a forest, okay, that are not man-made, or not man-made, but man-planted and planned, are very random, wherever the wind took the seeds. Bears, when they're not mating, are also quite random. They don't live together. Bears like to be isolated by themselves. And so when you think of Yogi, if you've heard of him, the Walker bear people named, we have a black bear that's been roaming Walker both last fall, and he's been spotted this spring again. He does random distribution. So he could be randomly on Alpine or somewhere closer to the Blandford Nature Center. His pattern of movement is really quite random, just looking for food and spaces that are safe. Next idea is population growth. So we know what a population is. We know how populations could exist. Now, what about their growth rate? So sometimes we call this the rate of natural increase, and we're going to use the letter R to represent the growth rate. So that is the difference between the number of individuals born each year and the number of individuals that die each year. So to calculate this, we're going to take births minus deaths divided by the total population. So an example of a problem I might give you is there's 50 births in a year, 10 deaths, and there's 100 individuals in that population. So you would set it up doing 50 births minus 10 deaths, that's 40. Divide it by 100, the total population, that would mean the growth rate is 0.4, okay, which is positive. Even though it's a small number, it's still a positive growth rate, which makes sense. There is more individuals being born than there are dying, and so over time, that population is increasing. Let's look at an example. It's not on your paper, but where that's flipped, where there's only 10 births a year and 50 deaths, the population is still 100. I set it up the same way. I don't flip the numbers because 50 is bigger than 10. I still start with births. I have 10 births, 50 deaths. So 10 minus 50 is negative 40, and in this case, you would have a negative 0.4 growth rate. That means the population's declining. If you think about it, it still makes sense because if only 10 are being born and 50 are dying, you have a population decrease. Okay? Populations could live up to their biotic potential. That's the highest possible rate of natural increase for a population. So if there's no limits to that population, and we'll talk about things it depends on here, how high could that population increase? So it does depend on some things. Biotic potential is held back by the number of offspring that survive to a reproductive age. It's also limited by the amount of resources in a population, the number of mates, and the number of reproductive opportunities, as well as the presence of disease and predators. So the last subject here to kind of look at is mortality patterns. So we talked about growth rates. What about death? So mortality is the death in a species. And there's kind of three patterns that most species follow, one of those three. They're called survivorship curves. It is a graph of the number of individuals still alive at each age. And we're going to kind of group this into pre-reproductive, so like your infants, reproductive age, so like your adults, and then your post-reproductive age, like your senior citizens, okay, the older group. So type 1 is where most survive infancy but live a long life and die of old age. Humans are a perfect example of this, especially with modernized medicine. Most humans survive infancy, young adulthood, and tend to die of old age. Type 2 have an equal tendency to die at any age. So things like insects, rodents, or some birds here, okay, they could die very, very young. They could die at any point in their growth stage. They could also live to die from old age. But like insects, if a mosquito comes and bites me, it doesn't matter if it's a baby mosquito or like a gigantic adult senior mosquito. If it bites me and I can kill it, it's going to die. Okay, it has an equal chance. Rodents, if a hawk is swooping up top and sees it, it doesn't matter how big it is, it's going to be taken out of the population. Type 3 is where most die in infancy, but those that survive tend to live a long life. So things such as frogs and rabbits. So that's where there's like a ton of offspring. Like one single frog could lay hundreds, even up to thousands of tadpoles or eggs a year or a season. But very few of those actually survive to maturity. A bunch of them will get eaten by possibly other frogs, by fish, by turtles. They could freeze. They could be victims of chemical runoff from fertilizer. But a couple of them hopefully will survive. So that's where you see like a huge population of offspring, but very few make it to live a long life. The last chart we'll look at is age structure diagrams. These show the number of individuals at each age group. So it includes those three groups again: pre-reproductive, so like your babies, your infants, etc., your reproductive, and your post-reproductive. If the population is expanding, you're going to have large groups of pre-reproductive and reproductive age, like these first two graphs, the yellow and the red. That means they can still contribute to the population, even the pre-reproductive when they grow up, okay, and increase that rate. So these two are going to be rapidly expanding or slowly expanding, but you have that big base of pre-reproductive and reproductive age. Populations that are pretty stable are kind of more like columns going up. You've got some of reproductive age. You also have some infants of pre-reproductive age, but you don't have a massive difference in your population. Last one is declining, and that's where you see it really narrow down. Okay, you're going to have a lot of post-reproductive, some reproductive, and very few pre-reproductive. And that population over time is going to narrow and get smaller and smaller. So that's all the basics for this week. What else do you need to do? So submit the notes. There is an activity you can try at home, but more importantly, do the practice quiz so that you can go through those math problems, look at the vocabulary one more time, and then participate in a Google Meet. Both Tuesday and Wednesday, the Google Meet are going to be the same. It's going to be at 11 a.m. I'll post the link on Canvas under announcements. Join one of the two of those so that you can play a little review with us over this new content. So do the notes, do the practice quiz first, maybe try the activity, but do those before you join that Google Meet so you know what's going on. But if you have any questions, shoot me an email. We can email back and forth, or we could Google Meet one-on-one, and I'll get you what you need. Thanks.